From now on, we live in a world where man has walked on the moon. It wasn't a miracle. We just decided to go. Jim Lovell, Apollo 13. And that's somewhat appropriate for our class today on our view from the garden, because we're just gonna go. So today, I want to cover 4 questions. Sort of, what is our GPS coordinates in the universe? What is our postal address in the universe? How did we get here? What was the sequence of events that brought us here? And how can we know what the universe was like in the past? And can we see the entire universe? So to go after the first question, what is our postal address? I invite you to take a look at this image right here. This is from a National Geographic image. And we, of course, are on the Earth, orbiting the sun. And that fact has been probably drilled into your head since you were a child, because it's not obvious that the Earth goes around the sun. In fact, if you were asked to prove that fact, you might be hard-pressed to do so. But at the end of this course, you'll know that very well. And it was also one of the great revolutions, intellectual revolutions in human history, of the Earth going around the sun. So the Earth and our solar system, the topic of this course, is part of a local cluster of stars, as shown in the second box there, of about 40 to 80 stars in our local solar neighborhood. Then moving up in scale, that is all part of the Milky Way galaxy. Milky Way galaxy is about 100,000 light years across, and if you don't know what a light year is, that's okay. We're going to cover that in a few minutes as well. But basically, it means that it takes light 100,000 years to go from one side of the Milky Way to the other side of the Milky Way. Moving up in scale, the Milky Way itself is part of what is called the local group of galaxies, and there's about 40 galaxies in this group. There are 2 big boys in this local group, our galaxy, the Milky Way, and Andromeda, and those 2 are on a collision course. So in about 5 billion years, Andromeda and Milky Way are going to collide. They're going to merge together. And it's also, in 5 billion years, that's about how much gas is left in the sun to power the sun. So 5 billion years from now is going to be a pretty interesting time, because the sun will be dying, galaxies will be colliding. It's going to be fun. It'll be cool. It'll be interesting to see. Then our local group of galaxies is then, again, part of a larger structure of what is called a cluster, or superclusters of stupendous size, that are regions where there are more galaxies than on average, and so we're part of that. Virgo, for example, is part of our local supercluster of galaxies. And those superclusters, and then if you go back and you look on the very largest of scales, which you can see in this image, is that the universe at the largest scales has this very filamentary, lacy-like patterns, where galaxies are like pearls on a string, pearls on the bead, and then in between where those galaxies are, there's these tremendous voids where there's hardly any galaxies at all. And so it has sort of this lacy pattern to it on the very largest of scales. So this is sort of our GPS coordinates in the universe, our view from the garden, of course being the Earth. What is our postal address here in the universe? And so how did we get here? How did we land in this house? How did we land in this garden? So the universe started about 14 billion years ago. That's how old the universe is. And in the Big Bang, only 2 elements were created in the Big Bang, hydrogen and helium. And both of those are odorless, colorless gases. There was no carbon, there was no oxygen, there was none of this. So where does all this good stuff come from, the stuff of life, the stuff that makes you and me? Well, where this stuff comes from is from stars. It's the stars that are the element factories. They're the ones that make the carbon in your bones, the oxygen that you're breathing, the iron in your blood, the carbon that makes the apple pies. They make the periodic table. They make you and me, and hence that we are star stuff. Okay? We are an integral part of the universe because we have been created from it. And so over time, as stars go through their life cycle, they live, they die, and then it's the galaxies that act sort of like the great mixmaster of inside of a galaxy. So stars go through a cycle. It's called the star-gas-star cycle. Stars are born, stars die, and every time they die, they spit out a certain amount of new elements, of new isotopes. And those new elements then get mixed by the great galactic mixmaster of the Milky Way and other type galaxies that disperse those elements throughout the galaxy. So over time, the Milky Way and other galaxies slowly build up their inventory of heavy elements like carbon and oxygen and calcium and uranium and other things. And eventually, out of those two odorless, colorless gases that came out of the Big Bang, life pops out. So that's kind of the joke. Hydrogen and helium are odorless, colorless gases. Put it in a box, and 13 billion years later, people pop out. And so this image shows how we go from the Big Bang up through the formation of the first stars, the formation of the first galaxies, the creation of the elements as we go, until we are 13.7 billion years later, looking back through time toward the origin of the Big Bang. Okay? So, can we actually see what the universe was like in the past? Oh, absolutely. And it relies on a very fundamental, basic fact, that it takes light a certain amount of time to go from A to B. So for example, when you go over to the wall and you flip on the light switch, to you it looks almost instantaneous that when you hit that light switch, the light from the light bulb comes down and hits your eye. So it's very, very fast because the distance is relatively short, but it does take a certain amount of time for that light to go from the light bulb into your eye. Now, as you make that distance bigger, the time that it takes light to get to you takes longer. So, for example, let's take the sun. When a photon, which is a little packet of light, leaves the surface of the sun, it takes 8 minutes for that light to go from the sun to your eyeball. So when you're looking at the sun, you're not seeing the sun as it is in its frame. You're seeing the sun as it was 8 minutes ago. And that's just because it takes light 8 minutes to get from there to here. Go out to Pluto now. So it takes light about 1 hour, 1 light hour to go from Pluto to our eyes. So when we see Pluto in a telescope, we're seeing Pluto as it was 1 hour ago. Now extend the distance out. When we take a look at galaxies that are millions of light years away, it has taken light millions of years to travel to get to your eyes. So when we see those galaxies, we're seeing them as they existed 1 million years ago. And so our telescopes are very much real time machines. By looking out in space, the farther out you look, the farther back in time you look. And so one of the goals of astronomy has been to push back the boundary of how deep you look in space, and hence how far back in time you can see. And so can we see what the universe was like in the distant past? Absolutely. And it's only limited by the technology that you can put on your telescopes, and then once you push back to a certain point, there's this great fog bank called the cosmic microwave background radiation, which is all around us. It's in this room. You can watch it on your television if you want. And that's as far back as we will see with optical and radio telescopes. Okay? So can we see the entire universe? Yes. We can see the entire universe that light has had time to reach us. So we just said that the universe was about 13.7 billion years old. And so the only things that we can see is where light has had time to travel those 13.7 billion years to reach us. So we distinguish between the observable universe, which let's say, just for visualization purposes, is a sphere with a radius of 13.7 billion light years. So we have the observable universe, and that itself is embedded in the entire universe. So the entire universe is much, much, much bigger. And the observable universe is the only thing that we can observe because it's all that light has had time to reach us. So every year, the sphere gets a little bit bigger, and we see a few more galaxies. We see a little bit farther back in time. We encompass more and more matter as time goes on and light has had time to reach us. But our observable universe is probably a very small fraction of the total universe that we see. So in this course, we're going to come across several definitions, use some terms, and so I just want to walk through a few minutes what some of those terms are and what they mean and how we'll use them in this course. So the first one is a star. A star is a large glowing ball of gas that generates heat and light through nuclear fusion in its core. And what's the nearest star? The sun. The sun is a star, right up close and personal. And so the sun is an example of a star. A planet is a moderately large object that orbits a star and shines primarily by reflected light, right? The planets don't generate their own light and heat through nuclear fusion. All they do is reflect the light from their parent star back to who's ever observing it. And so there's three criteria to be called a planet. One is that it orbits a star. Number two is that it's large enough for gravity to make it round. So that distance is about 200 kilometers or so, when gravity will start to overtake the strength of rock and turn it into something round. And perhaps most critically is number three, is that the planet has cleared its neighborhood of other objects. And so it's number three where Pluto falls down. Pluto has not cleared its orbit of other objects out in what is called the Kuiper Belt. There are larger objects than Pluto out in the Kuiper Belt, and so this created quite the dilemma. Are we going to have 10, 11, 12, 13, 14? How many planets are we going to have? And so it was these definitions that were put in place, and as a result, Pluto is no longer classified as a planet. It is classified as a dwarf planet. But that's not such a bad thing, because Pluto, instead of always being the oddball out in the solar system, now has a family. It's got a family of other trans-Newtonian objects, of things beyond Neptune, out in the Kuiper Belt, and we'll be talking about that. And of course, these definitions also apply to exosolar planets, which is part of this course as well. We have a moon or a satellite, which is any object that orbits a planet. We have an asteroid, which is a relatively small rocky body. And then we have a comet, which is a dirty ice ball, a relatively small icy object that orbits a star. So once you go from solar systems, then you have collections of stars and their solar systems. So we have a solar system, which is the star and all the material in it, so the planets and all the asteroids and all the comets and everything on out to there. Then stars, in an aggregate sense, once you put about 100 billion of them together, like the Milky Way, become a galaxy. And so a galaxy is a great island of stars. It's an island universe of stars containing a few hundred to a few billion stars in them. And they all orbit a common center. And if you're worried or curious about what's in the middle of the Milky Way, it's a black hole. So we have a big old 3 billion solar mass black hole in the center of our galaxy. Then, as we saw in our GPS coordinates, you aggregate up until you get clusters of galaxies and superclusters of galaxies, which are clusters of galaxies. And then you have the observable universe, which we talked a little bit about there in our GPS coordinates in our view from the garden. So we have two primary distance units that we'll be talking about in this course. One is called the astronomical unit, which is abbreviated AU. And it is the average distance between the sun and the Earth. It's about 150 million kilometers, okay? And so we'll be talking, so that by definition, the distance between the Earth and the sun is 1 AU. The distance between the sun and Mars is about 1.5 AU. And so the AU allows you to talk in relative terms. Mars is 1.5 times farther from the sun than Earth, rather than specify the actual distances. So that is one of the distance units that we'll be talking about. The other distance unit that we'll be using in this course is called the light year, which is the distance that it takes light to travel in 1 year. And by extension, we can go things like the light second. How far does light travel in 1 second? We just had an example of light minutes, where it takes light from the sun 8 minutes to go from the surface of the sun to the Earth. And finally, we're going to have terms relating to motion within the solar system. On the one hand, we have rotation, okay, which is an object spinning about its axis. So for example, the Earth rotates on its rotational axis every 24 hours, once a day. Rotation is distinct from revolution or orbiting, which is the motion of one object around another object. So the two, rotation and revolution or orbiting, are very different things. Keep that in mind. Thanks. Bye-bye.